Hey everyone, welcome back to another explainer. Today, we're taking a pretty wild journey together. We're going to start from the massive global scale of our everyday lives, zoom all the way down to the invisible atomic level, and then pull right back out again to see how these tiny structures shape our entire modern world. We're talking about the chemical building blocks of life, hydrocarbons. You can basically think of them as the invisible Legos of our universe. So, let's get right into it with a quick question to get our gears turning. What do a camping stove, a plastic water bottle, and the paved road right outside your house all have in common? Honestly, on the surface, absolutely nothing. They look different, feel different, and serve totally different purposes. But at the molecular level, they share the exact same fundamental architecture. To see how that's even possible, here's our roadmap for today. First, we'll meet the hydrocarbons, then we'll uncover carbon's rule of 4. Explore chains, branches, and families, and cover naming the invisible. Finally, we'll look at properties and reactions before wrapping up with fueling our world. Let's get going. All right, Section 1, meet the hydrocarbons, the literal chemical foundation of modern life. Now, I know the word hydrocarbon can sound kind of intimidating, but they're actually brilliantly simple at their core. By definition, a hydrocarbon is the simplest type of organic compound because it's made entirely of just two things: carbon atoms and hydrogen atoms. That's literally it. No secret ingredients. And we get these vital raw materials straight from the earth in the form of petroleum, natural gas, and coal. Moving on to Section 2, carbon's rule of 4, the atomic building blocks. Listen, if there is one single thing you take away from this entire explainer, it's the number 4. This is the absolute golden, unbreakable rule of carbon chemistry. Because a carbon atom has exactly 4 valence electrons, it always, and I mean without exception, forms 4 covalent bonds. It shares its electrons with other atoms to get stable. Basically, every carbon atom acts exactly like a 4-sided Lego block, just waiting to snap together with other pieces to build incredibly complex structures. So how do those blocks actually connect? Well, carbon can share its electrons in 3 main ways. First up, single bonds, which make molecules called alkanes. These bonds are strong, and they actually let the molecule rotate freely. Next, we have double bonds, or alkenes. These are stronger, for sure, but they restrict rotation. They kind of lock the molecule's shape into place. And finally, triple bonds, known as alkynes. By sharing 3 pairs of electrons, you get the absolute strongest and shortest possible bonds. Oh, and alkanes? We call those saturated, while alkenes and alkynes are unsaturated. Okay, Section 3, chains, branches, and families. This is how structure dictates function. Here's the really crucial part. It's not just about what atoms you have, it's all about how you arrange them. Take a look at this comparison. On the left, we've got a straight chain alkane, like normal butane. It's arranged perfectly linear, which gives it a larger surface area. Those molecules stick together more easily, resulting in a higher boiling point. But then, on the right, look at a branched chain alkane, like isobutane. It has the exact same chemical formula, but it branches out. That makes it super compact, with less surface contact, and boom, it has a significantly lower boiling point. Literally just changing the physical shape completely alters how it behaves in the real world. Which leads us perfectly into what we call a homologous series. You can just think of this as a chemical family. They all share similar chemical properties. But the trick is that every successive member of the family grows by exactly 1 carbon and 2 hydrogen atoms, a CH2 unit. So by snapping on just 1 more CH2 block at a time, we seamlessly go from methane up to ethane to propane and right on to butane. All right, on to Section 4, naming the invisible, the universal IUPAC language. Now you're probably wondering, how on earth do chemists keep track of all these variations without losing their minds? Well, they use this sort of universal decoder ring, and it's built entirely on these super basic prefixes. Memorize these and you can instantly decode the world around you. 1 carbon gets the prefix meth, 2 is eth, 3 is prop, and 4 is but. After that, it just follows the geometry shapes you already know: pent, hex, hept, oct, non, and dec. So an alkane with 8 carbons, obviously it's octane. See, it makes total sense. There's just this pure, elegant logic to it all. The IUPAC naming system gives us 5 simple steps to name any alkane, which creates this perfect global consistency, whether you're in a lab in Tokyo or New York. Step 1, find the longest continuous chain of carbons. Step 2, number that chain from end to end. Step 3, find any branches sticking off the main chain. Step 4, give those branches a position number. And finally, Step 5, Write the whole name out alphabetically. It is a completely foolproof roadmap. Let's actually test drive this decoder ring together. We need to name this specific branched alkane. Following our exact steps, the longest chain has 4 carbons, meaning our base name is butane. We number the chain, and hey, look at that, we spot a 1-carbon branch, a methyl group, attached right to the second carbon atom. Put the whole shebang together, and the universally recognized name is 2-methylbutane. I told you, it really is that easy once you know the secret. Section 5, Properties and Reactions. Let's look at how hydrocarbons actually behave in the real world. Let's zoom out just a little bit. Notice how the sheer number of carbons directly dictates the state of matter? Molecules with 1 to 4 carbons are incredibly light, making them gases at room temperature. But start adding more carbons, say 5 up to 17, and the intermolecular forces really ramp up, pulling the molecules closer together into liquids. Add 18 or more, those forces lock the molecules tightly into solids. Oh, and one more thing. Because hydrocarbons are nonpolar, it doesn't matter if they're a gas, liquid, or solid, they are never going to dissolve in water. But without a doubt, the single most important reaction these molecules undergo is combustion. When you mix a hydrocarbon with oxygen and add a spark of heat, you trigger a reaction that spits out carbon dioxide, water, and just immense amounts of energy. I mean, this exact equation literally built the Industrial Revolution. But, it comes with a pretty serious warning label. If there isn't enough oxygen present, you get incomplete combustion, and instead of just CO2 and water, you end up producing highly dangerous carbon monoxide and dirty soot. And finally, Section 6, Fueling Our World. We're looking at the impact of hydrocarbons on society and nature. So here is the exact answer to that question we asked at the very beginning. What do the camping stove, the plastic bottle, and the road have in common? Very specific carbon chains power every single one of them. Methane gives us cooking gas. Propane heats our homes. Butane fires up our lighters. Gasoline and diesel drive global transport. And those heaviest solid bitumens, that is quite literally the asphalt making up the roads we drive on. But we really have to look at the full picture here. The reality of hydrocarbons is a massive trade-off. Yes, these molecules are absolutely essential for our modern fuels, the synthesis of critical medicines, and producing all our plastics. Yet, the extraction and massive combustion of these incredibly energy-dense molecules are directly tied to some of the most critical environmental challenges our planet is facing today. The downsides of our heavy reliance on hydrocarbons are huge. Severe air pollution, ramping up the greenhouse effect, global warming, and those devastating localized oil spills. But right alongside those problems, science and engineering are pushing hard for solutions. We're developing cleaner fuels, transitioning toward renewable energy, and using brilliant tech like catalytic converters to literally strip pollutants right out of the exhaust. Which leaves us with a pretty provocative thought to ponder. As we keep trying to power our future and, frankly, fix the pressing realities of global warming, how exactly are we going to evolve beyond the fundamental carbon chemistry that built our entire modern world? It's a colossal challenge. But hey, by understanding the basic building blocks, just like we did today, we actually empower ourselves to engineer a totally new reality. Anyway, thank you so much for joining me on this explainer. Keep asking those great questions, and I'll catch you in the next one.